He is about to speak. Okay, good evening, everyone, and welcome to the CGU Earth Data webinar. And today it's our great honor, pleasure to have our speaker, Professor Alessandro Aiuppa, speaking with us from the University of Palermo, Italy. So today's talk will be on the topic of the deep carbon from the evidence of the volcanic gas constraints, as well as geochemical analysis and thermodynamic modeling. So with that, I will give you the rest time to Alessandro. And normally we speak for about 45 minutes, then leave some time to interact with our other participants. So as we talked about before, that we're going to record this talk so that for people who missed the webinar would like to check it out so that they could take a look at it. Okay, with that, Sandro.
Okay, thank you very much for your kind invitation. It's my pleasure to give this webinar on one of my favorite topics, carbon and volcanoes. And so I'm gonna start with a brief outline of my talk. I'm gonna start with describing the motivations that have led people to start a new project on carbon, and especially on volcanic emissions of carbon dioxide. And I will then review some key highlights of this project, especially focusing on our new estimate of carbon dioxide emissions from the most strongly volcanic gas emitters on Earth. Then I will briefly discuss the implications on the importance of diffuse degassing in terms of the global volcanic carbon dioxide budget and the role continental rift volcanism may have in such a process. And I will end up this part of the talk just by reviewing our new estimate of the total global volcanic CO2 flux from subaerial volcanism. And then in the second part of my talk, I will concentrate on trying and provide you constraint on the carbon content of the upper mantle, especially the mantle source of oceanic island and continental rift volcanism, trying to convince you that carbon concentrations may increase downward in the upper mantle. And then I will draw some conclusions. So why carbon to start with? I think it is rather obvious. We are in a period in which carbon dioxide concentrations are rising in the atmosphere. So we as geologists need to look back into the geological past and look at periods where carbon dioxide concentrations have been similarly high or much, much higher. And the bad news is, as you know, that there is a very close link between periods of high CO2 concentrations in the atmosphere and greenhouse periods of our planet. So high CO2 means high temperature in our planet. And this link between high CO2 concentrations and hot climate is very clear if you focus on the Cenozoic. And again, cold Cenozoic climate corresponds to periods of very low carbon dioxide concentration in the atmosphere, while hot greenhouse periods are coeval with high CO2 concentrations in the atmosphere. So there is a clear link between atmospheric carbon and climate. And obviously, in a geological past, this link has been regulated by the global carbon cycle, this continuous cycle of carbon dioxide in and out our planet. And I think we all agree that volcanic emissions in the oceans and in the atmosphere are the key ingredients of such a process. Fact is, however, that there are large uncertainties in the carbon cycle. This sketch is from a paper 10 years old now. And what I'd like you to concentrate on is on the numbers, and especially in the fact that we are pretty much ignorant on the amount of carbon that is released by volcanoes. There are large uncertainties, even though we have been trying to measure carbon dioxide emissions starting from the 80s last century, when the first techniques became available to measure sulfur emissions from volcanoes, and therefore carbon emissions just by combining together compositional data with SE2 flux data. So we have 40 years of record of carbon dioxide emissions, but still we are facing large uncertainties. Here in this diagram on the bottom, I'm comparing all the available estimates of carbon dioxide emissions from volcanoes starting from 1982 and dating back a few years ago. And as you can see, estimates range from a few tens of teragrams of carbon dioxide being released every day up to several hundred. So what is true? What is the real magnitude of carbon emissions from volcanoes? And in order to try and overcome this limitation, the Deep Carbon Observatory started. The project itself started to try and answer several missing and unknown problems related to carbon in Earth. And it was a very large program, it's a 10 years program funded by the Sloan Foundation, and more than 1,000 scientists participated for more than 50 countries. And the volcanic gas community entered the project thanks to the efforts of the late Eric Howry. Eric came and visited us in Kamchatka during one of our regular meetings and tried to convince us that it was critically important to try and refine our understanding of carbon dioxide emissions from volcanoes. This slide here is a sort of summary of where we were at the beginning of the project. So the state of the art was that we had a very limited data set. Only 33 volcanoes had their carbon dioxide emissions measured in some way. Emissions data were very discontinuous, sporadic data were large emitters in the Mantle area, in PNG, in the Solomon, and many other remote regions were still uncharacterized for their carbon dioxide emissions. So we made a number of actions during the project. We start with deploying a network of volcanic gas sensing instruments in 15 key volcanoes just to try and look at short-term fluctuations of composition. And even more importantly, perhaps, we conducted field campaigns in more than 70 volcanoes, presently uncharacterized for their carbon dioxide emissions, so that volcanic gas database increased from slightly more than 30 volcanoes measured for carbon to more than 100 at the end of the project. And in order to do so, we also had to refine our, sorry for that. We also had to try and refine techniques for measuring carbon dioxide emissions, which included also the measuring of carbon dioxide emissions using drones and volcanic gas instruments mounted on drones to try and measure the CO2 emissions from the most remote and accessible volcanoes on Earth. And this is the way the data look like. So you can launch a drone with your volcanic gas unit inside. You can approach the volcano, get into the plume, and measure the composition of the gas in real time. So I'm going to try and review some of the key highlights of the project, at least to my mind. One of the most significant conclusions of the project was to refine our estimate of CO2 emissions from the strong volcanic gas emitters on Earth, what I will be calling as SVGE volcanoes. So basically we have around 900 volcanoes, active volcanoes in the Holocene, and a large fraction of those are actually dormant, or they are just producing calderas and thermal systems, while about 90 of them are active. They are strongly degassing, they have open vents, they have magma exposed to the atmosphere, producing a lot of gas. And it is on these strong volcanic gas emitters that we concentrated on the project. as they are the dominant source of sulfur and carbon to the atmosphere. As you can see in this UV camera-based video, they exhibit strong visible SU2-rich plumes. And even more importantly, these plumes can also be seen from space using satellites. And in this very important study in 2017, Simon Kahn and co-worker were able to identify the 91 strongest volcanic gas emitters on our planet. They were able to rank these volcanoes and to sum up their emissions to conclude that globally, volcanoes release about 23 teragrams of SU2 every day. In the decade, we were able to convert these SU2 emissions into carbon dioxide emissions from knowledge of volcanic gas compositions for all of these strong volcanic gas emitters. And this is our top 20 list, and perhaps more nicely, a global map showing the 91 strongest volcanic carbon emitters on our planet. And by summation, we have estimated that these volcanoes release between 36 and 39 teragrams of carbon every year. One second point we made in the project is that diffuse degassing is a key process. So the fact is that we have these active volcanoes that are releasing carbon through plumes, but we also have these dormant calderas and these hydrothermal systems that are releasing carbon in a more diffuse, silent form, such as degassing ground or soils that are releasing a lot of carbon dioxide. And within the project, we were able to try and refine our understanding of the diffuse carbon emissions, and we got the big surprise that diffuse degassing here is perhaps the largest unknown and perhaps the largest term in the sub-area of carbon global budget. So apparently diffuse degassing is releasing even 2 to 3 times more carbon than is released by plume from the most active volcanoes on our planet. And this plot here is just showing what we had at the end of the project. So our current best estimate for carbon emissions from global subaerial volcanism is in the order of 140 and 170 teragrams of carbon being released every year by volcanoes, predominantly in the form of diffuse degassing, as shown here by this yellow bar. The third important surprise was that diffuse degassing is likely to concentrate in continental rift context. There has been work that has been made trying to look at the areas that are releasing more carbon diffusively from grounds and from springs. And it appears that the areas that are releasing more gas are tectonically active areas of the world in extensional regime. So apparently when you have extension, you have more carbon being released, to the point that continental rift volcanoes such as the East African Rift might be releasing 80 teragrams of carbon every year. And globally, the contribution of continental rift can be more important. Work has been done trying to understand why continental rift is so important in terms of carbon transfer. And the current interpretation is that subcontinental lithospheric mantle underneath rifting craton is very carbon rich because of long-term metatomatism mediated by carbonated silicate melt or carbonated melting cells. And these metasomatized lithospheric mantle is there bilaterally at the border of the rifting craton where it melts to produce carbon-rich melts, eventually carbonatites at the Nillengai, and more importantly, large diffusion, carbon dioxide emissions at the margins of rifting craters. And if you look at globally, there has been work proposing, like this work by Wong and workers in 2019, from Big Carbon Observatory as well, suggesting that globally continental rift could be the large part of the puzzle, releasing several hundreds of teragrams of carbon every year. And if you look to the past, Wong et al. Were able to demonstrate or suggest that over the last 200 million years, continental rift may have produced between 40 and 70% of global carbon emissions from volcanoes. So they might be dominating the global carbon emissions over time. On the other end, plume-related volcanism, which is shown here in green, appears to be much less significant, perhaps like contributing 10% of global carbon emissions today and in the geological past. At the same time, however, it is very important to concentrate on plume volcanism, on oceanic islands, because they are their best access point to the deepest part of the mantle, to the convective mantle, where the majority of carbon is likely to be stored. And I just want to remind that in our top 10 list of volcanoes, at least one OEB volcano, Kilauea, clearly stand up in conjunction with Radongo and Yamura volcano in the East African Rift. They are likely to be currently the largest source of volcanic sulfur carbon on our planet. So continental rift and oceanic islands are very important. And this is why we decided to concentrate on trying and understand what the carbon content of the mantle source of continental rift and OEB is. So why are they producing so much carbon? What is the carbon content of the mantle source feeding this kind of volcanism? And of course, the answer might come from melting inclusions. As you know, melting inclusions are tiny droplets of silicate melts that are trapped inside crystals as they form inside Earth. And eventually you can measure carbon and water concentrations in these melting inclusions, and you can understand entrapment pressure of these melting inclusion. And even more importantly, you can understand how much carbon is dissolved in silicate melts prior surface discharge, eruption, and degassing. The problem is that unfortunately, melting inclusions typically trap already degassed melt. This is the case of Bardarbunga volcano in Iceland, and where melting inclusions have been studied intensively to show that entrapment pressures of melting inclusions are in the range between 5 kilobars to surface. So this means that melting inclusions are trapped where magma is already stalling in the upper crust or in the upper mantle and the crust about 10 to 15 kilometers. But eventually, the magma is rising from much, much deeper, for more than 40 kilometers in the case of Bardarbunga volcano, which means that with melting inclusion, we are losing a large fraction of the ascent path of magma. So we don't have any melting inclusions trapped between 40 and 10, 15 kilometers, where the majority of carbon is degassing. So as carbon has very low solubility in carbonate in silicate melts, the majority of the carbon will be lost prior to melt inclusion entrapment. And they will thus be missed from the inclusion record. We proved the degassed nature of melting inclusions in this work in which we reviewed melting inclusion work done on middle oceanic ridge basalts. As you know, these basalts are erupted deep in the ocean where pressure is high enough to prevent degassing, so that these undegassed melting inclusions and undegassed morphs can allow us understanding what the carbon to niobium ratio of the mantle is. So in this plot, CO2 is in the Y scale, niobium is in the X scale. Niobium is typically used because there is a very similar compatibility relative to carbon during mantle melting, and therefore we assume there is no limited fractionation between carbon and niobium during peritotite melting. So in principle, if you have undegassed melting inclusions, based on them, you can define the mantle carbon to niobium ratio of the mantle. But unfortunately, if you then plot melting inclusions, they clearly plot in this diagram on the right portion of it, which means that they do exhibit much lower carbon to niobium ratios than the mantle proxy, which means that they have lost the majority of their carbon prior to entrapment in the melting inclusions. So melting inclusions are degassed, and this is why we as a gas community decided that we need to look at volcanic gases. There's Nyiragongo volcano, and this is just to show that volcanic gases are transporting the volatiles that are lost to the gas phase like magma and are missing in the melting inclusions report. So what you don't find in the melting inclusion will be gassed by volcanoes in the gas phase. So in a sense, it has been long been said that volcanic gases are sort of telegrams of the Earth interiors, and so perhaps they can be used to try and understand what the volatile content of the Earth mantle is. It has long been known since the 80s of the last century that volcanic gases from continental rift and OEB contest is very unique in terms of carbon, water, sulfur composition. So basically, arc volcanoes will be plotting here in this orange area because they are typically enriched in water due to delivery of water from the subducted slab, while continental rift and OEB volcanoes are definitely less water rich, more carbon rich, but they do exhibit this very large spread in carbon to sulfur ratios from more than 50 to less than 1. So why? How can we interpret this range of carbon to sulfur emissions in these cases? This is why we selected 12 volcanoes. These are the only 12 volcanoes for which we have high quality, high temperature magmatic gas information. 6 volcanoes are alkaline, shown in dark blue, and 6 are toleically transitional, shown here in light blue. And what we did is that we compared for each volcano the time average carbon to sulfur ratio in the gas phase against the strontium to samarium or strontium to neodymium ratio in the rocks that were delivering that gas. And this is where the big surprise came. So what we did find is that there is a very nice correlation between the carbon to sulfur ratio in the gas phase and the strontium to neodymium ratio in the source rocks, which implies that the level of carbon enrichment in alkaline systems relative to toleitic systems scales well with the level of strontium and other large ion lithophile elements enrichment in the same magmas. I wish to point out that very similar correlation was found using other trace element proxies. And what is it telling us? The key conclusion here is that since strontium to neodymium, strontium to samarium are conservative ratios, these elements are not volatile, they are not degassed. So if these ratios scale well with the carbon to sulfur ratios, then it implies that even carbon to sulfur ratios in the gas phase are representative of initial conditions in the magma of parental melt ratio in the source mantle. So carbon and sulfur are degassed, so they can be fractionated because of selective extraction from the magma due to contrasting solubilities in magma. But what we do find is that they are correlated with non-volatile elements, and therefore their time average ratio for each volcano must be representative of the source, which means that you can use the carbon to sulfur ratio, you can multiply it by the parental melt sulfur content in magmas, which is known thanks to melting inclusions, to quantify the CO2 content in parental melt. So we did so for toleitic volcanoes and for alkaline volcanoes, and we find that toleitic volcanoes typically contain 0.1 to 1 weight percent CO2 in their mantle source, while alkaline volcanoes are more carbon rich. They contain between 1 and 7 weight percent carbon before being released. And in order to test the quality of our measurements, we compare our parental melt CO2 contents with niobium again, and nicely our results fall within the mantle array, while melt inclusions data do not. And the same was found for barium. Barium is another conservative element sharing a similar incompatible behavior compared to carbon. So again, we have an additional test that our CO2 carbon estimates are definitely more precise than melt inclusions might be suggesting. So this can be applied to many important topics in volcanology. So for instance, our carbon to sulfur trace element relationship can be used to predict the CO2 content of past eruptions. This is, for instance, the example of Lucky eruption in Iceland in the 18th century. Was one of the largest historical eruptions on Earth. It released a lot of sulfur and perhaps a lot of carbon, but we are ignorant on CO2 emissions from these volcanoes. But what you can now do is that you can use the strontium to neodymium ratio of the Lucky melt inclusion. You can combine it with our global gas rock association, the equation is shown here, to convert the strontium to samarium ratio into a carbon to sulfur ratio that you can multiply by sulfur in the melt inclusion to quantify the parental melt CO2 content of this past eruption, which will be pointing here at a higher range of the likely melt inclusions nicely. But perhaps the most substantial application make is to try and use our results to make inferences on the carbon content of the Earth's upper mantle. So eventually, if you have knowledge of CO2 in parental melts, you can use knowledge of melting fractions in the upper mantle, which we were able to estimate based on zirconium modeling, to convert parental melt CO2 into carbon concentrations in the upper mantle. And the range of carbon mantle concentrations we were able to find range between 100 and 700 parts per million. And most significantly, if you plot our estimated carbon concentration for different volcanoes against the depth of initiation of melting, which we were able to quantify using commonly used geobarometer, then what you do find is that there is a very nice increase in carbon concentration paralleling the depth of initiation of melting, which allows us to suggest that carbon concentration may be increasing the depth of melting in the upper mantle. Eventually, you can use this Darwin increasing trend of carbon concentrations, and you can integrate this equation here, this regression equation, over the entire depth of the upper mantle down to 200 kilometer depth to estimate that the upper mantle may contain 10 to the 23 grams of carbon in total, with a mean carbon dioxide concentration of slightly more than 350 parts per million, and the confidence interval we have been found. And this is a very important conclusion, as we know that carbon in the upper mantle is a driver of carbonated peridotite melting. So this plot here from Dasgupta is comparing the dry peridotite solidus with the solidus of carbonated peridotite. So we know if we have carbon in the mantle, then the mantle will melt deeper and earlier than in dry conditions. And Dasgupta and co-workers were able to demonstrate that if the mantle contains 100 to 300 parts per million carbon, then we might expect 0.1 to 1% weight percent melt followed by melting of carbonated periodicite. But if, as our data suggests, the mantle contains between 400 and 700 ppm carbon in the 100 to 200 kilometers depth range, then eventually mantle melting can extend to higher melting degree. A few weight percent of melt can easily form in the mantle if the mantle is so carbon rich. So eventually we demonstrate that carbon is likely to be a substantial geodynamic driver in the upper mantle. And the final application is that we can use our gas versus trace element relationship here to try and identify the chemistry of metasomatic melts in the upper mantle. So as you know, we believe that carbonated silicate melts and carbonatitic melts are the most significant metasomatic agents in melts. They transport carbon and large elements such as strontium in the mantle. So eventually we can try and demonstrate, or at least test, if our global distribution here can be explained by a model in which a metasomatic melt is added to the depleted mantle in variable proportions to obtain a range of enriched mantles that then melt to produce the rocks and the magmas we see to the south. So in our model, we assumed that these metasomatic melts could have a kimberlitic to carbonatitic composition, and we used the range of naturally erupted kimberlitic and carbonatitic melts to make guesses on the CO2, sulfur, and strontium range these metasomatic melts could have. And these stars here are showing the end-member compositions we assumed for the carbon, sulfur, and strontium concentrations of these metasomatic melts. And with these guesses, we used a melting mixing model. I don't want to enter into the details of the calculations, but I can answer questions if you are interested. But in a way, we used a model in which we use melting and mixing at the same time to try and fit our gas rock population. And based on this fitting, we are able to propose the addition of a few 8% of metasomatic melts similar in composition to natural kimberlites can explain the array of gas and rock composition we see at the surface. And more importantly, we can estimate the full trace element signature of the metasomatic melt. So our estimates are shown here in red for the carbonatitic assumption and in white for the kimberlitic assumption. And importantly, the model composition is very similar to the composition of natural kimberlites, which seems to suggest that carbonated silicate melts are the most likely metasomatic agents present in the upper mantle. And the slide here is a sort of summary of our conclusion. We believe that carbonated silicate melts are transporting mantle from the deep mantle into the upper mantle, where they enrich the mantle in carbon. So the mantle will melt in response to these high carbon concentrations. And eventually, the higher the carbon, the deeper the mantle will melt, so that the deepest melt formed at the base of the African craton, for instance, would be more enriched, as shown today by Yagongo and Odoyengai that came in Africa, while the carbon is less carbon rich, then it will melt very shallowly, and it will produce the carbon depleted composition of middle oceanic fluid basins. And my conclusions to end up. So decade has brought significant advances in our understanding of volcanic carbon dioxide fluxes, even though I'd like to say that there is still much to do. we estimate that between 140 and 170 teragrams of carbon are released every day by subaerial volcanism, with the majority of the carbon being unexpectedly released by diffuse degassing. And there is a large fraction of carbon that is probably released away from volcanoes in areas of tectonic extension. And this extensional regime in continental rift volcanism is probably the largest source of carbon, and it could be releasing today 0.3 to 0.4 gigatons of carbon every year, even though there are large uncertainties and much remains to be done in trying to understand what this tectonic CO2 flux is. We have also found that the gas carbon to sulfur ratios are globally associated with the trace element signature of the source magmas. And based on this association, we have found that continental rift oceanic islands basalts contain between 0.1 and 7 weight percent CO2. Based on what we have been able to find that the source mantle may contain several hundreds of parts per million carbon, which, if true, implies that carbon is likely to be a substantial main geodynamic driver, forcing carbonated peripheral melt to melt much deeper and earlier than previously thought, especially if, as our data seems to demonstrate, carbon increases downward in the upper mantle. And I wish to conclude thus by saying thank you to the Deep Carbon Observatory and all my contributing authors. This work has been possible thanks to collaboration with many, many people around the globe and in Italy. So thank you to all of them, and thank you to you for your very kind attention.
Okay, thank you very much, Alessandro, for your talk. Now it's time for our audience to ask questions and interact. And here's one question from Ziqi that, thank you very much for your talk. And what do you think of the carbon fluxes coming from the bottom of the subcontinental lithospheric mantle compared with the carbon fluxes from the upper mantle?
So the implication of our work is that the carbon enrichment would be the largest underneath rifting cratons. So eventually, if you have a cratonic area and you have time, and you have enough time, that area of the globe will progressively enrich in carbon, so that when this stable area is fragmented by continental rifting, then a lot of carbon can be drained by continental rifting. And so I'm tempted to say that the subcontinental lithospheric mantle is likely to be one of the largest sources of carbon in our planet. If you compare carbon emissions from the depleted mantle, which you can estimate looking at carbon fluxes from middle oceanic ridges, then eventually the carbon flux from middle oceanic ridges is likely to be a small fraction, like 30% of the global carbon budget. The global carbon budget is likely to be dominated by continents, subaerial volcanism, and diffuse degassing from continental rifting that are eventually fed by subcontinental lithospheric mantle.
Okay, next question, please. Okay, I have a question. Out of curiosity, it is plotted in earlier part of your figure of the hydrogen, sulfur, and carbon ternary in terms of the gas composition. So I'm curious that although it's not shown in this work, that from this global volcanoes, that could you give any of the constraints on the mantle hydrogen or mantle carbon water ratio?
Yes, this is possible. This is something we haven't attempted yet. And I think you are talking about, let me find it. There you go. I think you're talking about this plot, correct? Is this the plot you're talking about?
Yes, yes, yes.
Okay. So yes, eventually you could use this plot to try and extend our conclusions to water as well and to the hydrogen content of the upper mantle, which is something we haven't attempted so far. The reason for that is that water is a very problematic element in volcanic gas science. The reason is that a large fraction of the gas data we do have in hands have been contaminated by meteoric fluids prior to collection. So in a sense, the water content of volcanic gases, with a few substantial exceptions that you do see here, tend to overestimate the real water content of parental melts. And of course, we could do that. We could play this game, but we have to be conscious that we may end up with overestimating the real water content of the mantle simply because the majority of the gas data we have in hands might have been contaminated prior to collection by some extent of meteoric fluids. I tend to say that as it is clear that intraplate volcanism is producing much less water than hard volcanoes, then eventually the level of this contamination is not that strong. So it would be nice and important to try and make a calculation we were proposing, which is something we have been planning to do for quite a bit of time.
Okay, actually, I have another question. Could you turn to the last figure of the Nature Geoscience paper? Sure. The carbon concentration in the mantle as a function of depth. I think by that plot.
This one?
Oh, so sorry, the second last one. Second last figure of the paper, with the horizontal axis of carbon concentration and the vertical axis of depth. Yes, okay, this one. Actually, I have two questions to it. So number one, that for the depth, I think in your paper you mentioned about that use the barometer or it is calculated by melts. But in my recollection,
we use temperature. We model temperature, liquidus temperature with melt, and then we use that temperature in the Butyrka-Joule barometer, using temperature and parental melt composition to infer pressure of initiation of melting. That's what we did.
Okay, I see. Okay, I see. So you didn't use any like the mineral barometer. Okay, that's okay. And for this plot, you got to take a look at it. Then I see these triangles and diamonds with a depth of about 60 to 90 kilometers. And then they have extremely high carbon concentrations. So are those points, okay. Because this, this too. Yeah. Triangles and diamonds.
These one are Erebus and Etna.
So this two looks really standing out from the rest of them, right? Because if carbon concentration that increases with a function as a function of depth near the mantle, then these 2 points definitely they're in the middle part of it, but have extremely high carbon concentration.
Yeah, correct. So I'm not sure I got your message right, but yeah, these are the 2 points. These are alkaline systems. So we believe that alkaline magmas are formed by low degrees of melting of an enriched carbon source, of course. And so if you have high pressure melting, then you will melt the mantle for a few weight %. You will end up with an alkaline melt with a lot of carbon dissolved in it. So these Erebus and Etna are definitely alkaline systems. And at the same time, you have Kilauea plotting here, which seems to suggest that even in an oceanic intraplate setting, if you have a lot of carbon in the mantle source, much higher than it has been previously suggested using melting collisions, then you will end up with melting at 3 gigapascals or more, so much deeper than you would expect in the absence of carbon. And of course, these points are forcing our trend. At the same time, if you move back to Iceland, Iceland will be plotting somewhere here. The mantle is much less carbon rich, it's much closer to the little mantle, and therefore melting will occur very shallowly. And this is where the Icelandic volcanism will plot. So I wish to point out also that in fitting the data, we were also using the main composition of the depleted mantle, which is shown in green. So I would say it's not just a matter of a few points, but it's the entire population that is fitting the data in a quite robust way.
Okay, we have participants asking further questions in the chat, and Chow and Professor have 2 questions. First, he's curious about whether it's feasible to use carbon dioxide concentration of magmas combining melting collisions and the degassing curve of the carbon dioxide with depth.
Well, I think that's the opposite. So to be honest, what we now need is that we need more work trying to make these relationships statistically more robust. So my point is we only have 12 volcanoes for which we have data. So eventually we need to try and complete this compilation and make it more robust. So we need more gas information. If you have gas information, you can estimate CO2 content in the parental melt. From the parental melt, you can end up with calculation of carbon in the source mantle that you can finally plot here to try and see if our correlation is correct or not. We believe and know it is statistically significant with the data we today have in hands, but it would be highly desirable to add even more significant, just adding more data. For instance, we just returned back from a volcano in the Canary, where we measured the carbon concentration, the volcanic gases, the carbon to sulfur ratio. So we now have an estimate of the carbon content in parental magmas and in the mantle for parental mantle, and nicely it would be plotting somewhere here. So as we acquire more data, we have the same for the new eruption in Iceland that just ended. The new eruption plot somewhere here. So our target is to try to test the solidity of our model, just trying to get more information on more unexplored volcanoes. And the second question is, what is the mechanism of CO2 degassing in rift? So volcanoes are producing a small fraction of that carbon. So eventually what people have been demonstrating is that the majority of the carbon dioxide is released in a diffuse form through soils and partially from springs, but these are very arid countries, of course. So the majority of the gas is just released in a very silent diffuse form through soils at the margin of the rifting cratons. So for instance, if you go in Tanzania and you measure soil degassing, then you will find that a lot of carbon is released by soils, much more than in the ground areas. So the real problem here is that there are just a few spot areas that have been measured so far. So the fluxes have been based on large extrapolations of small measured areas. So we are in need of refining these estimates, trying to extend observations to wider areas and to make the extrapolations much more robust than they are at this stage.
Okay, here are another two questions. And the first one is about, could you explain again in detail of why the whole rock strontium cerium has a very good correlation with the gases, carbon dioxide and sulfur ratio?
Okay, so why this correlation? So there are two substantial things in this plot. One, on the Y scale, you have ratios between two volatiles in the gas phase. And in the X scale, you have the ratio between two non-volatile species in the melt. So the only way you could have a relationship is to assume is that even though carbon and sulfur are volatiles, so they will be released in the gas phase as the magma is decompressed and volatile solubility decreases. So even though these species are volatiles, then if you measure volcanic gases time after time, the carbon to sulfur ratio in volcanic gases will be representative of carbon to sulfur ratios in the source mantle. Otherwise, you wouldn't find any correlation. So in a way, carbon to sulfur ratios are conserved during degassing, even though the two species can fractionate during degassing. The second important information here is that if you have a positive correlation, then it means that you must have a similar source of carbon and strontium in the mantle. So that the process that are enriching strontium and are other large ion lithophile elements in the mantles are the same processes that are enriching carbon in the mantle. So our interpretation here is that the mantle gets enriched because metasomatic melts are metasomatizing the mantle. And these metasomatizing melts will be carbonatitic or kimberlitic melts. And as this plot shows, carbonatitic and kimberlitic melts are very high in carbon and very high in strontium. So you have these melts that are very rich in carbon and incompatible elements entering the upper mantle, metasomatizing the upper mantle, and enriching the mantle in carbon, strontium, and other large ion lithophile elements. These enriched mantle will then melt to produce the gas rock correlation we see at the surface. I hope it's clear enough now. If not, please let me know.
Okay, and also following question that, do you think that the Asian craton source have higher carbon concentrations compared with other tectonic sightings?
Say it again? You think that?
Yes, it is in the chat. Do you think that the craton source or the cratonic mantle have higher carbon content than carbon in other tectonic, than the carbon concentration in the mantle at other tectonic settings?
Yeah, for sure. For sure. This is what we are suggesting. For instance, we are suggesting that the carbon source underneath Miragongo volcano might be containing 700 parts per million of carbon. This is the highest concentration we have found. And eventually, the carbon source underneath Oldoino Lengai is more tricky to estimate. This is because we don't have good gas information about Oldoino Lengai yet, but for sure, Oldoino Lengai volcanism is producing carbonatitic volcanism, and therefore the mantle source will be even more enriched in carbon. And this model is well consistent with meteorological study that has been looking at the mineralogy and chemistry of the magmas that are erupted on the margins of lifting cratons. And the only way to produce those magma melodic composition of kimberlites or carbonatites. The only way you can produce those magmas is to have small degrees of melting of a very carbon-rich source.
Okay, another question from Master Chi, that what do you think could be the possible mechanism of how the carbonated rocks in the craton transferred to the rift area?
This is, let me find the figure. Yes. This is from a work by the group of Tobias Fischer and who works in Nature last year. And what they've been proposing is that as you have a cratonic area and you have rifting at the border of the cratonic area, then the cratonic metasomatized mantle will be advecting laterally and vertically to be concentrated toward the margins of the cratonic area itself, where the extensional regime will favor the compressional melting, then ascent of magmas, eventually the eruption, but the majority of the gas will be delivered by degassing of unerupted magmas along the margin of the continental rift. So if you look at this map here, all the inner Lengai is here, which is all the carbonated volcano we have in hands, but all along the margins of the crater, of the craton, we have this dark brown area where CO2 concentrations are very high. And this area of very high CO2 concentrations and fluxes in soil is interpreted as a phase expression of degassing of magmas formed by lateral advection of the cratonic lithosphere underneath the rifting craters. This is not my own work. This is work made by Tobias Fischer and co-workers.
Okay. Do we have more questions for our participants? Okay, I think that's about our seventh day. So thank you very much, Andrew, for your talk. And thanks to everyone for your participation in this webinar. And see you next week. And have a nice day, Andrew.
Thank you. Have a nice day. And thank you for inviting me. See you next time.
Okay, bye-bye.
Bye.